Hello, my name is Emily Brown from the Department of Mechanical Engineering at the University of Minnesota, and I will be presenting on the preliminary design of a muscle-powered exoskeleton for users with a spinal cord injury. Damage to any part of the spinal cord is known as a spinal cord injury. Each year, there are about 17,730 new spinal cord injury cases occurring annually in the United States. A wheelchair is often the selected mode of mobility for these individuals. There are many disadvantages and adverse effects that they may face as a result of being in a seated position for prolonged periods of time. These effects include pressure sores, muscle cramps, muscular atrophy, and less efficient blood flow. To combat these adverse effects, it is crucial that people with spinal cord injuries exercise their legs, thus creating a need for an exercise method for those with spinal cord injuries to prevent adverse effects of prolonged sitting by allowing the ability to stand and walk for short periods of time using one's own muscles. There are a variety of exercise methods currently available that those with a spinal cord injury may use. Motorized exoskeletons are lower limb exoskeletons with electric motors driving the joints with untethered power. They are heavy and the muscles are not being stimulated. Passive orthoses are externally applied devices used to modify the structural and functional characteristics of the neuromuscular and skeletal system. The gait can be slow and exhausting, which is just one of the high discrepancies between the gait of an individual without a spinal cord injury. Functional electrical stimulation devices work by sending low-level electrical impulses to the nerves, which signal the leg muscles to lift the foot. A walking aid is required, and the user typically experiences rapid muscle fatigue, and erratic stepping is common. Hybrid devices combine electrical stimulation with the lower limb passive orthoses to overcome some of the problems with pure FES systems. With our exoskeleton design, we are taking the hybrid device approach. The proposed FES-ESE generates initial motion through electrical stimulation of the quadriceps and stores excess energy in springs to assist with the completion of the gait cycle. The FES-ESE system is lighter than powered exoskeletons and provides additional health benefits because the power is provided by the user's own muscles. The proposed addition of a novel bidirectional clutch mechanism for joint control and a 40% reduction in weight are expected to remedy previous device shortcomings. The development of a wearable exoskeleton, as shown on the right, requires defining the desired gait motion. The synthetic gait cycle shown in the figure begins with the hip and knee joints flexed for the right leg, shown in red, and extended for the left leg, shown in green, which begins in the stance phase. From the flex position, the right knee joint is unlocked in the direction of extension, and the quadriceps muscle group is stimulated. The quadriceps stimulation produces more energy than required, and gas springs tied to the hip and knee joints capture and store excess energy. Subsequently, the user employs gravity to fall forward onto the now extended right leg, which enters the stance phase and supports the left leg as it enters flexion. The right hip joint is unlocked in the extension direction, and as the user pushes against a supportive rail, the hip joint is extended. Finally, in the swing phase, both the right knee and hip joints are simultaneously unlocked in the flexion direction, allowing the energy stored in the gas springs to release and actuate joint flexion. This returns the leg to the neutral position, where the process is repeated for the left leg. Energy storage elements explored in earlier versions include pneumatic cylinders, elastomer bands, constant force springs, and gas springs. Gas springs were selected for use in the FES-ESE for their reliability, repeatability, and lack of required maintenance. Gas springs have a high stored energy to weight ratio and long life cycle due to the lack of leakage and pressure losses. While their constant force behavior extends the accessible range of motion, the cylinder must be sized to individual users. For normal human walking and standing, muscles are continuously activated to provide torque for maintaining joint rotation. Duplicating this process with an FES exoskeleton would require continuous muscle stimulation, resulting in unsustainable levels of muscle fatigue. This can be overcome by implementing a bidirectional joint locking mechanism to allow rotation in one direction at a time, with opposing rotation locked to continuously provide the necessary holding torque against gravity to prevent collapse. Further work is underway to develop a more capable bidirectional clutch mechanism with active directional control. The redesigned FES-ESE is a novel hybrid exoskeleton that combines the benefits of a passive exoskeleton with functional electrical stimulation of the quadricep muscles. The exoskeleton is powered only by the user's own muscles. The lack of electric motors, high energy to weight ratio of the gas springs, and compact nature of the bidirectional clutch mechanism result in a 40% weight reduction over previous versions. Future work includes preliminary testing with users using a constructed physical prototype of the FES-ESE. Thank you.